Alright, so this will be the last tutorial before the reading week. I just want to do one more example on the directed graph DFS, which we kind of did with the first example yesterday. I have another one that's slightly more complicated. We can do it together. That's the only one I want to cover. And in that way, you get enough exercises for you to try it out throughout the reading week and also finish your assignment number 1. So as I said, after the reading week, we are actually going to generalize the properties about the colors for the vertices, either white or gray or black, and also about the time stamps for each vertex, namely the D for discovery and also F for finish, right? So this is something we'll generalize after the reading week. So hopefully you can take some advantage to really go over the 2 examples that we're going to do. We're going to finish, okay? And also I try to make the example a little bit slightly different format in the beginning, in the sense that I don't really give you the graph right away. It is something you will have to draw by yourself. All right? Okay, let's take a look. Okay. In case you already downloaded the tutorial instruction, let's say before 10 p.m., something like that. So I already updated that, right? Just in case, right? I want to show you the up-to-date version. The original one I kind of put up. I think that one there, I can save that for the assignment for you to try it out. So today we're going to try something more relevant to yesterday's lecture. Okay. So if you go to the lecture site, okay, I'll show you exactly, and then we'll start from there. All right, you can see for the instructions over here, of course, the starter page, the template, you have to download as well, right? I also updated that. Okay, this one here. All right, so we're going to do DFS run on directed graph. And this is the actual instruction. Let me make it a little bit bigger. And then let's now go over some very quick idea, and then we can start with it. So the question goes like this. We want to consider some directed graph, and the graph is actually not given to you visually right away. Instead, we give you the vertices and edges. So what you should do is to really draw all the vertices and draw the arrows as well. All right? Why don't we take that as the first part, right? And then once we agree on the graph, that's going to start with, and then we're going to do the second part, which is we're going to do some depth first search, and then we're going to keep track of, let me show you very quickly, right? So we don't need to revisit this. I can just concentrate on my iPad. We assume that we're still going to visit all the outgoing edges by using alphabetic order. And also the edges will be either discovery, back, forward, or cross. And we have to keep track about the discovery time and also finish time. And also we're also going to keep track about the stack as well. Right? So these are all the things we did yesterday. But this example here is just slightly more complicated. We can see more examples about back edge, cross edge, and forward edges. Okay, so this is something I would like you guys to take maybe 2 minutes. It shouldn't take longer than that. Take this graph specification like a pair, right? You got vertices, you got edges, visualize it. Okay? 2 minutes. And also, let's say this is a question that I will give you on the test or the exam. My tip would be, as you kind of draw maybe the first version, you might actually cross the edges somehow, right? Cross the lines. Try to get the first version done first, and then try to kind of judge to see how you can move around the vertices so that you don't really cross the lines. You'll make your tracing later much easier. Okay. And of course, when you are doing this in the test or the exam, you want to double check to really make sure this is the one to go with. Because if you got this initial graph wrong, all the answers later will be wrong. Right? Okay, why don't we wait for just 1 moment, okay? Hopefully it's not too bad. Basically, we got 7 edges And also we got, I think about 6 vertices, and we got 11 edges. Yeah. Okay, one more moment, and then we'll compare your answer with mine. All right, let's compare. Okay. Is that what you have? Let's double check together. A, B, C, D, E, F. A, B, C, D, E, F. Right? And then let's see edges. AB, AC, AD, BC, CA, DE, DF, EA, EF, FB, FC. All right? Agree? All right. Of course, it's unfair because I did it last night, so that's why I drew a little bit more beautifully, right? So don't feel bad, right? Okay, so let's now talk a little bit more about this graph over here very quickly, and then we'll get on to tracing it. That's the only thing I want to do today, okay? If we can finish earlier, we finish earlier. We'll see. First of all, we know that after, and also star vertex, which I didn't really mention explicitly, right? But we assume that it's going to be from A. Okay, star vertex. We got 6 vertices. And we know that the DFS is trying to build a tree. The DFS tree, which will be spanning, in this case. Of course, in general, which we'll talk about after reading week, in general, you might need more than one DFS runs to really cover all the vertices. But for this one here, we know starting from A is going to cover everything, right? Just make it a little bit simpler, just for now, okay? So the spanning one is going to contain exactly 6 minus 1, which will be 5 discovery edges. So eventually, you can expect that 5 will be the number of discovery edges. That means the remaining 6 edges, we got 11 edges in total. So the E here, we got 11 edges, right? If you count, it's exactly 11. So that means over here, we got back, forward, and also cross edges. We got 6 of them. Okay, just give you a little bit of look ahead. So eventually, we're going to get exactly 2 back edges, 2 forward edges, and 2 cross edges. So we can really see just more like an affirmation about each edge, right? So I think this example will be really worth our time before the reading week. All right, so 6 edges, we can look forward to it. And then, remember the t value. T will be the global timer. In the beginning, it's going to be 0, right? Given this particular setup, what do you think will be the maximum, the final t value that we will increment up to? And hints for you, think about the stack. Oh, you guys have answered. Yes, please. 12? Why would that be? Yeah, exactly. That's exactly right. Okay. So the t-value here, we can expect that when the DFS run terminates, t will be equal to 12. Okay. So the 12 over here is the number of vertices multiplied by 2, because each vertex is going to be push and pop exactly once. You don't push the same vertex twice. You don't also pop the same vertex twice. You don't do that, right? Just exactly once. So 2 times the number of vertices. Each vertex pushed and pop once. All right, that's something I want to just clarify. Right? Okay, let's now trace it. It's going to be a little bit more dense than yesterday, but I think today I will also let it go a little bit further, which I didn't really do yesterday, about how do you judge if one vertex is neither the ancestor nor descendants of one vertex, in which case we should get a cross edge. I didn't quite say that explicitly yesterday. I simply showed you the visualization of the DFS tree. We can see that a little bit today. I will still not really go to the 100% detail. That will definitely take some a little bit more time to discuss, which we'll do on Monday when we come back from the reading week. Okay. Anyway, just let's do it. Question.
Would it be incorrect to make like one edge that goes both directions, or is it like each edge can only go?
That's good. Yeah, I'm so glad you brought it up. Right. So I think it's Jody or Jada, sorry. Mixed with Judy, sorry. Jada, okay. So Jada's question was, let's say we got these 2 vertices. Is it allowed to go here and this here bidirectional? It's absolutely allowed. Because in the directed graph, the order of the vertices in an edge actually matters. So either you can say AC or CA. You might be a little bit confused with, I'm guessing, maybe when we talk about parallel edges, in which case it will be not simple, the graph. If we say AC here, we got another AC. But it's not the case over here. So it's totally fine.
But you cannot have like one edge that goes both directions. It has to be still 2 separate.
Yeah, exactly. So these 2 are considered separate edges. And even more interesting, as we'll see, one of them is going to be considered as back edge. One of them is going to be considered as forward edges. As long we'll see. Good. So they will definitely be treated differently. Okay. All right. Any other questions before I move on? Diego.
At the beginning, you mentioned that we're going to have 2 back, 2 forward, and 2 cross edges.
Yeah.
Because we have 6 edges that are not.
They also just happen to be for this example. I'm not saying always you're going to divide exactly by 3. Not really. Yeah. I'm just saying happen that with the way I designed for this example, I want you to see more instances for each category.
Right, but they don't always have to be equally distributed.
No, definitely not. It could be, could be that you got maybe more back edges than forward edges, but you have no cross edges. It's possible. Completely arbitrary for this distribution. You just for this case over here happen to be just nicely 2 and 2 and 2. Yeah.
And then my second question was, is there any advice you can give us on how to draw the graph so that we don't have any
cross lines? That one is not really about CS or software engineering anymore. It's about artistic judgment, right? So when I actually draw, the first, I would say somehow I kind of just draw A, B, C, D, E, F, and then as I go, I try to avoid crossing the line as I try to draw any new edge. If that's possible, I do it. Once I finish version 1, I would say that's almost about 80%, 90% perfect. And then I try to revise a little bit by moving around the vertices, right? Yeah. Maybe anybody who's very good in drawing can advise the whole class, right? We'll see. Okay. Anyway, yeah. Okay, let's now do the thing. Good. All right. And let me put that diagram here again, but I'll make it smaller. Right here. All right. And let's now try to set up the tracing artifacts. We're going to start with push and pop, right? We're going to trace the stack. So we get push and pop. Okay, because every vertex will be pushed and popped exactly once. You can expect there will be exactly 6 rows in this table. But we don't need to write it out just yet. But eventually, it should be exactly 6 for the push and 6 for the pop. And then we're going to have the table for the timestamps. Right here. Okay, so we have the T here. And, we have the vertices. We got A. So 6 of them. 1, 2, 3, 4, 5, 6. Okay. A, B, C, D, E, and F. And then I got D here, discovery. I'll write it down, just to remind you. And also F. So D here, discovery. And F here, finish. Okay. The giant table is going to be to keep track of the colors for the vertices. And timer is going to start with 0, and then we got 12, right? Push and pop for every vertex. So there'll be 13 rows in total. Okay, let's do it. Okay. Okay, I'll try to start from here. Okay, I think up to here should be okay. So the timer value eventually is going to grow. Oh, actually, you know what? Let me try this. 0. A little bit tedious, but I can do the same thing, right? You're going to be 13 rows in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? So this will be the T value, okay? Let me just double check. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, I actually got one more, okay? All right, good. Okay, and then we got 3 columns there. We got white color, gray color, and black color, okay? Okay, call in here. Call in here. Okay, I think I can make it a little bit compact, so I can write more comments. Okay, I think that should be good. Yeah, the lines over here are not really strictly necessary. I think just for me to present, just easier for us to see. Okay, and then we got different colors. In the beginning, white. And then we got gray. And then we got black. Okay, very quick check. What does each color really mean? When I say vertex is actually white. Just, yeah, white, what does white mean? They have not been pushed yet. They have not been visited just yet. Good. That means their D value is undefined. Good. What about gray? Oh, just maybe try. Diego, gray.
It's been visited, but it has not been finished yet, so it's right now on the stack.
Yeah, exactly, in the stack. So that means the discovery time is defined, but not the finish time. Good, very good. Black. Judy. Yeah, exactly. It's finished, so it's been popped off the stack. That means the finish time is recorded. Good, very good. Okay, so you guys, you can refer back to the notes yesterday, or you can see the slides. Okay. All right, so let's now see, and then we got a stack right here. All right, right here. All right, so I think we got everything we will need. And then this part here, I'm actually going to use it to write some comments, okay? I'm also going to put something over here about something called DFS tree. Okay? There are so many things to really keep track. I'll try my best to make sure every step is actually completely recorded, okay? But if I really forgot any part, please do let me know right away, okay? All right, in the beginning, the time value here is simply 0. Every vertex is white. A, B, C, D, E, and F. Nothing gray, nothing black. That's the beginning. And time value is simply 0. Good. And the DFS tree is undefined. And we assume that we actually start with A right here. That will be the start vertex. Okay, let me write it down explicitly. So this is the start vertex, which will become the root of the DFS tree. Okay, so the first step, we're going to turn the color of A to be gray, meaning that it's now visited. Consequently, we're going to push A to the stack. Increment the time to be 1, so that means discovery time for A is 1. And A is no longer white. So B, C, D, E, and F. So A is now gray. And something we didn't quite do exactly yesterday, but let's now do it in sync. Think about the DFS tree is now being formed as well. A, the root, is right here. Like a one-node tree for now. The tree is going to be expanded whenever we whenever we can identify a new discovery edge. That's the principle. Okay. Okay, I think we got everything here. And from A over here, we don't have a choice. Oh, actually we do. Either we can go for B or we can go for D. Agree? Alphabetic. Let's go for B. Okay. So what we do is this edge over here is going to be discovery. The first edge. That one there is going to discover vertex B, which is going to turn that into gray. And we should really push B to the stack. And then the counter should be incremented. So we got C, D, E, and F, and gray will be A and B. Okay? So previously we tried to change A, and now we have changed B. Okay? And then the timer for discovery for B should be 2. So also good. And then the DFS tree has now been extended from here to B. Whether it should be a left child, right child, doesn't matter, because DFS tree, it should be a general tree, not binary tree necessarily. Okay. Okay. All right, so we got everything here. Good. Let's now move on. Okay. Next, the top of the stack is B. That's the only way, right? That's the only outgoing edge. All right. So what we do is we try to have another discovery edge right here. That would be number 2, which is going to discover C. Currently it's white, so that's why it's discovery edge. We're going to turn that into gray. Consequently, we're going to push C to the stack. And then we're going to increment the counter by 1. So now D, E, F remain to be white, but C has now become gray. Right here. And we also effectively extend the DFS tree to C. Similar to yesterday, similar. You just want to get more proficiency in doing this, right? Now here comes interesting bit here, right? So now you can see that from C here, we are not touching that bidirectional arrows. We definitely should take the CA, right? AC here is not applicable since we're going from C, right? So what we're doing here is from C to A. Okay, so that one there is going to be 3. If that's not a discovery edge, that means we don't need to do any push or pop, meaning that we shouldn't really need to increment the counter. We shouldn't need to. And then, so at this point, we actually identify something that's not discovery. Okay, so let me just circle this time here. This is a time when we identify CA. But we need to see exactly what this kind of edge is. And of course, from the previous one, I forgot to put 3 here again, right? Just be careful. You got to make sure you put all the information at each step. So what kind of edge is this? We got back edge, we got forward edge, we got cross edge. Right? Yeah, go ahead first. Back edge because?
It's going back to a predecessor.
Predecessor or ancestor. Ancestor, good, very good. Yeah, awesome. So I'll try to maybe show you from 2 cases, right? So what we're having here is going from C to A. So from C to A, right here. You can see the D value. If you're going to some D value that's strictly smaller, and the vertex itself is not finished yet, you're basically going to an ancestor. All right, I'll write it down. So this is a back edge, number 1. Okay, so I'll put back edge, number 1. Okay. Okay, I think it should be safe. Let me put right here. Okay, back edge number 1. So for that one there, CA. Oh, if you see the diagram here, we go from C to A. We're pointing back to the ancestor, right? Well, that's another way to see that. So really pointing back, so back edge. That one there is B1. Okay? CA is a back edge because the discovery time for A, the destination, is strictly smaller than the discovery time for the source, C. And also A is still active. How about not finished? All right, so was it good? Good. All right, so that's good. I think we got everything here. I think it will be very important for you to know at what time did we actually identify each back edge, cross edge, and also forward edge. That might be something I will ask you, right, in the test. Okay. All right, next one. And you can see now the top of the stack is still C. C. As far as C is concerned, the only outgoing edge is this one here, which has been handled. What should we do? Pop or backtrack, right? That would be the more formal term, backtrack, right? You're basically running out of all the outgoing edges to go further, right? All right, so at this point, we should really backtrack, which means we're going to do pop. What that would do is we're going to pop C from the stack. The consequence is we're going to change the color of C to black. Okay. Let me now do this one here properly today, a little bit differently. So C here is now going to turn to black. All right. And then, so you can now, this is the point that you can see all the 3 colors in the graph, right? You got white color, you got gray color, you got black color, right? Gray colors are all the vertices that's currently on the stack, right? And then we got to increment the counter. to record. Number 4, over here. So that means we're going to remove C from the gray color. So what we have is, so the white color doesn't change, D, E, F, and then C should be popped. A, B, and then we put C in the black. Okay. And for the tree, you don't need to. You don't need to remove C, by the way. C is there, right? It's really part of the tree. You don't remove it. Okay. All right, and then the finish time, right? So the finish time for C should be number 4. Okay. The finish time for C is 4. You can think about C is the very first vertex that has been push and pop already. Okay. All right. And the next one. Anybody? Suggestion. What's the next one? Tian Tian, go ahead. Yeah, that's pretty good because B is now the top of the stack, so we have to see what choices we have for B, right? That's awesome. That's exactly right. Good. So if you look at, okay, always remember, if you're not too sure what to do next, always look at what's the top of the stack. It tells you what to do, right? So the top of the stack is B. As far as B is concerned, there's only one outgoing edge, but that one there has been handled already. So we got no choice. We got to pop B. So what we do is we're going to pop B, in which case we have to change the color of B from gray to black. Okay, and then we should increment the counter. And then we just do number 5. And then we are removing the B, right? So D, E, F, still the same. A is now the only one that's gray. The only one that's gray. A, only gray vertex, that means only one, only A in the stack, right? You can see the correspondence, okay? And then what we have is we got C, and then we got A. Oh, beg your pardon. C and B. Because we're removing B. Okay. And let's record the finish time, which will be 5 for B. Yeah, let's try to maybe, I'm pretty sure eventually we could call everybody. We got enough, yeah. Anybody who's trying to put their eye contact away from me, I should choose them. Okay, yeah. Would you like to give it a try? You can skip, that's okay. I don't want to embarrass anybody. You can give it a try.
Like the next spot A is going?
Yeah, I agree, because now the top of the stack is A.
Yeah.
So what should we do about A? We go to D. Right, exactly. So here we see that A has 2 outgoing edges, but A to B has been identified as discovery already. So go A to D. Exactly, good. Thank you. Okay, so what we do is we're going to discovery edge. So what we do is A to D. All right, over here. And then, so that's going to be number A to D. Did I? Oh, actually, A to C, right? Yeah, I made a mistake. Remember here, okay, that's good. I'm so glad you guys stopped me. Yeah, yeah. All right. Guys, that's why you got to be very careful. All right, so what I did wrong was, you can see here, as far as A is concerned, I can either go to D or go to C. Alphabetic order. So I should go to C. Okay, very good, very good. Apparently, this is already black, C. So that means it cannot be discovery edge. It's got to be one of the 3 kinds, right? But now we got to decide what it is. Okay. So this will be number 4. By the way, number 3 is back edge. We'll put a B here. Okay. And then at timing number 5, we are now considering AC. And you can think, okay, so now any suggestion? What should be the type for AC? Yeah, go ahead. It's pointing to descendant. That's right. That's forward edge, right? Okay, let's now see. The most obvious way to see that would be A to C, right here. From A to C, pointing to descendants, right? So I would say descendants, so that's a forward edge, F1, okay? So what I would do is I'm going to say it's from A to C. Another way for you to see is A from A to C, the opposite direction over here. Let's look at the value very quickly. If you go from A to C, C relative to A is the descendants. And the descendant has already finished. That's also part of the condition. Okay, we'll talk more about the properties about D and F on Monday. All right, I'll write it down. So this will be forward edge number 1. So F1. That's going to be A to C. It's a forward edge because over here, since we're going to a D value 3 that's strictly larger than 1, and also the destination here is finished already. So we're going to a descendants. Okay. Because the destination C was discovered later than A. And also C is already finished. Okay, it's a forward edge. Okay, good. All right. So now you can see that, oh, this is also forward, right? So back to your question earlier, when we had this bidirectional edges between the two nodes, it's definitely legitimate. And turns out, one is back edge, the other one is forward edge. But somehow if we kind of fix the maybe outgoing edge of visiting order, things might change. But for this particular fixed order, it's that way. Right? Okay, very, very good. All right, so let's now go further. Good. You want to try again? What should we do now? We'll go to D, exactly. We got only one option there, right? A to D. Yeah. Discovery. Let's finish this AD here, and then we'll take a short break. We're exactly halfway, okay? So what we do is we're going to go for AD. That one there is going to turn the unvisited D into visited, into gray. And that one there is going to push D to the stack. And then we're going to increment the counter from 5 to 6. That one there is going to move D here to the gray. Right? So that means we got EF, and then we got AD. Okay? So D is a new discovery. Okay? And then the black edges, so the black vertices remain the same, C and B. All right? And we got to record. The discovery time for D is 6. So we got, so far, the counter 1, 2, 3, 4, 5, 6. 4 pushes and 2 pops. So that means we got 4 edges discovery, exactly. Okay? If you look at, yeah, we got that exactly. Yeah. Any question so far? Good. Why don't we take a very short break, and then we'll continue the rest, okay, after short break. All right. So there's something I forgot before the break, but it turns out to be good timing. Talk about it right after the break. When timestamp is number 6, we discover D right here. So that's why we put D to the stack. All good. but we didn't really expand the tree. Let's think about how we should really put D. Should we put D here, here, or here, right? The decision is actually very simple because D was actually discovered from A. So that means this edge over here should be another branch from A. So that means D should be right here. All right, it's a different branch. So that means this will be just another branch. So that means later on, if there's any edge that will try to go across different branches, for example, I'm just making that up. If I want to go from D to B, for example, it will be a cross edge. If I want to go from D to C, that will also be a cross edge. Right? I'm just saying, right? Good. All right, so now we are now dealing with D right here. Oh, question first.
For the DFS, is the discovery edges non-directional then? Because we want to draw the direction for the...
Oh, I see what you mean, yeah. Because the way we're gonna, well, since the way we draw the tree already kind of suggested the order of the discovery edge, right? Because I go from, since B is kind of below A, so I know I really got an edge from A to B. I know exactly what you mean. But I think for this tree here, we understand what's going on. Yeah. Mm-hmm. Yes, that's good. All right. Okay. Please. What should we do now? Any idea? We go to E. Okay, that's good. And would that be, what kind of edge is that? Discovery. Thank you. That's good. So the top of the stack is D. D here, we got either go to E or F. This edge is not outgoing, so we don't consider it. Go alphabetic, so we're going to go for E. Great. That's good. Okay, let's now do that. Oh, by the way, the previous discovery edge is number 5, right? So here we go for another discovery edge. That will be number 6. Okay, that should be straightforward. So we basically turn that into gray. And we push E to the stack. Increment the counter over here. So that means only F is unvisited, the only thing that's white, okay? And then we put the E to be also gray. And everything else remain the same. Okay. And let's record the time. And it should be 7 right here for E. All right, and then the next. Shall I give it a try? Yeah, go ahead. F from where to where? Tell me exactly. E to F, yeah, good. So what kind of edge is that? Yeah, good, simple case. So here we got E here. And then we got 2 choices. Oh, actually, you know what? We can either go to A or we go to F, right? Alphabetic order. Be very careful. All right, guys, be very, very careful. I can even put the bold text in the test question to say alphabetic order, right? But I gotta just remember, okay? Because if you just got one step wrong, it will be cascading, right? Yeah. All right, let's now do E to A. Apparently, that's, oh, what kind of edge is that? Back edge. Okay, we'll see. Okay. So by the way, from the previous one, again, I forgot to really extend. We got D to E, right, in the previous one. And what we're having now is from E to A. E to A. Going back to ancestor, back edge. Very good. Thank you. Good. Let's now do it. Okay. Okay, E to A, turns out it is a back edge. Number 7, a back edge. Okay, and then let me try to, so from E to A, this is the second back edge. Back edge we're seeing today. I'll say that's B2. Okay, or if you want to see it from here, from E to A, okay, this is B2. Okay, let's look at B2. Very similar argument as B1. So going from E to A, because the destination discovery time for A is strictly smaller than discovery time for E, right? Oh, just got the opposite, beg your pardon. So E here, 7, strictly larger than 1. And also, A, not yet finished. Okay. You might already get a sense. Ancestor should really finish later than descendants. But don't worry, I'm going to summarize the property next Monday. But for now, just focus on the example. Make sure you can do it. If there's anything you think you can observe and you believe there's a general property, write it down, right? And then maybe you can confirm on Monday. Okay. Okay, that's a back edge. And that one is done. Okay. Okay, so let's now move on. Next. Yeah, please. From where to where? E to F? Yeah, I think, yeah, we have no choice. Right, good. Thank you. What kind of edge is that? Discovery? I agree. For those of you who have to be called, later one will be more difficult, by the way. Okay, we'll see. Yeah. All right, E to F. Discovery. And that one there will be turned to gray. All right. And then we're going to push F to the stack. So you can see that right now, every stack has been pushed. That means we have already visited all the nodes. Some of them has been finished, some of them has not been finished. That's the only difference. Okay. So after that, we're going to, okay, let me expand the tree first. So that means we go from E to F. So this will be the DFS tree so far. And then we're going to increment the counter from 7 to 8. Okay, 7 to 8. And that one there is going to turn F to gray. A, D, and then E, and then F, right? That's newly discovered. Okay, we still get only C and B popped so far. And then we got to record the time, which is 8. You can see the discovery time is defined for all the vertices at this point. Okay? There's one thing I forgot to annotate again. So previously, when we did EA, we discovered that when the timer is 7. Okay, when you redo the exercise, you can double check. Okay, I just forgot to annotate. Okay, so over here, 7 here is when we actually identify EA as a back edge. Okay. Okay, I think that's good. All right. Okay, so next one. Oh, you want to? No. I want somebody else. Yeah. Anybody would like to volunteer before I call? Yeah, good. You seem to be volunteering. Yes. What should be happening here? First of all, what's the vertex that's right now active? F. Okay. What choices do we have?
Or we could go back to C.
Oh, go back to C. Yes. Can we also? Yeah, exactly. Be careful. So it seems like for F, we got 2 outgoing edges. We got either B or C, right? Okay, awesome. Oh, what kind of edge is that?
Back end.
Back edge? Okay, I would suggest another way, another way for you to see that. Let's say try the FB on the DFS tree. If you go from F to B, are we going across different subtrees?
Cross edge. Yeah.
Cross edge, right? And then I'm gonna say something a little bit new today about cross edge. I'll try not to go like a full extent for mathematical property, but I'll give you some intuition. Okay, let's now do that one there. So currently it's F right here. And then we're going from F to B. Apparently it's not discovery. So F to B. Right here. Right here. Okay, of course this one here is number 8. And this one here is number 9. Turns out this is a cross edge. Let's do what we did yesterday, and I'll give you some new insights. Okay? So if you look at from F to B, it's really going from F here to B over here. We're going across different subtree. Right? And F to B is right here. F to B right here. And then turns out this is a cross edge. But now, how do we tell? If you look at the DFS tree, it's obvious because you simply go from F to B. However, algorithmically, is it possible to look at other information other than just the tree? Okay, apparently you guys already know. Okay, maybe. Go ahead, yeah?
If you're going to a node that is already finished and the discovery time is less than what you're already at, then it's a cross edge.
Yeah, that's good, that's good. Basically what you're saying is, we are talking about D and F for each vertex to be some interval. If the interval I'm talking about does not overlap with another interval, that means they are in different subtrees. Okay, that's something, don't worry, I'll try to visualize even in more detail in a summary way on Monday. But for now, I'll make it more explicit for you, okay? First of all, let's now write this down, okay? So this one here will be C1, cross edge number 1, okay? Cross edge number 1, we're going from F to B. It's a cross edge. Let me write down the reason here, and then I'll visualize that a little bit. It's because the finish time of the destination B is strictly less than the discovery time of F. And at this point, B is already finished. Okay, that's the reason. But let's now visualize it. Okay, I'll draw that here. Thinking this way, you can see for B here, we already got 2 and 5. Discovery of B and the finish of B is 2 and 5. And think about B here is right here. It's already done at this point. After it is done, we are now looking at another vertex that's in another branch, which starts strictly after B is finished. Okay? So the way to visualize it is, after this, we got the discovery of F being 8. You can see it goes strictly after the finish of B. Okay? They don't overlap. If the interval don't overlap, that means they don't belong to the same subtree. Or you can say that F here is neither ancestor nor descendants of B. That's another way to say that. That's also what you see on the slides. Okay? There's another scenario where the interval may not overlap, just another way. It's kind of symmetric, but we'll make it more complete on Monday, right? Today just want to get intuition. Okay, so here we got non-overlapping. Okay. Okay, let's do another one. Also in timer 8, we already identify FB, right? FB already, all right? All right, next one. Would you like to give it a try? Do you want to? Yeah, please.
Yes, we go from F to C.
F to C, I agree. So now, what kind of edge is that?
Cross.
Another cross edge, I agree. Can you just briefly justify why that would be a cross edge?
Well, because the time of finish of C is 4
And the start time for F is actually after that, right? Exactly, very good. Thank you so much, right? That's good. Yeah, let's write it down. I think that's exactly right. All right, so we'll go from F to C, and apparently that's not discovery. So we're gonna do F to C right here. That one there is just another cross. Okay. And for that one there, it's going to be C2. Okay. I'll also visualize it at the same time. Okay, just one moment. So we go from F to C. It's basically just another cross edge from F to C right here. Right here. All right, so that's cross edge right here. All right, no push, no pop. And then F to C, I can just do another one here, right? F to C. If you look at that here, C here has the finish time that is strictly smaller than the discovery time for F. That means F is only discovered after C is finished. So that's a strict definition for cross edge. Good. 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 So C2, FC, cross. Because the finish time of C is strictly less than the discovery time for F. And C here is already finished. All right, good. Now C2. Okay, C1, C2. 1, 2, 3, 4, 5. We got 5 like a non-discovery edges already. We're expecting one more. Question.
Does the order matter? Like the order of the discovery, like the way you write it? You know how like you wrote discovery of A is less than discovery of C. Let's say I swap it, does it matter? But as long as I change the less to greater than.
Right. So it will work. Actually, so basically we're saying that, let me get to that exactly the inequality side, maybe a little bit later, because now we're just using these examples only. But we can generalize it to say for two intervals to be not overlapping, there could be two possibilities. So why don't we talk about it, a little bit later. Yeah.
Okay, so wait, I just wanted to double check. F to D would be a back edge, right?
With F to D, so you cannot go from F to D.
If it was possible.
Oh, if it was possible? Okay, let's see, from F to D. I can check very quickly. So if I want to go from F to D, yes, that will be a back edge, because go back to ancestor, if that's the case.
Would we lose marks for not putting B finish or C finish in our justification if FB and FC exist?
Say it again?
Would we lose marks for not putting B finish or C finish in our justification if we already put FB is less than DF because FB exists?
I know what you mean. So I would say this one is more like intuitive, like a notion just for today. I'll talk more about like how you should really write it formally, maybe when we get to the mathematical. I see exactly what you're concerned about. Yeah. Good. All right, let's now move on. All right, so also at timer number 8, we also identify FC. Okay. Good. Next. Over here. Yes, please. Please. Yeah. What should we do now? You may want to look at the top of the stack. It's F. Okay, so now, as far as F is concerned, what should we do? Well, we already got cross edge, right? You can see we got FB, FC already handled. So what should we do now? Seems like we're done with it. So when we're done with it, what should we do? Pop it, backtrack. Okay? Yeah. Yeah, so you definitely gonna, yeah. And then we go back to E in the next iteration. Think about it. Okay, good. Awesome, thank you. So what we do is, right here, the top of the stack is F. As far as F is concerned, you can see all the outgoing edges have been handled. Okay. Oh, by the way, the previous one should be number 10. Again, I forgot. Okay. So now we're going to pop F off from the stack. It's going to be turned into black in its color. And we're going to remove it from the stack. F. Get rid of it. And then the timer should be 9 right now. And A, D, E remain to be there, but C, B, and then F is the new black vertex. Right here. Okay. Okay, let's record the time. So it's going to be 9. All right. Awesome. All right, so next one. Yeah, I'll try not to call the same person twice. Barbara, would you like to try? Give it a try.
Okay, so going back to E.
I agree. What should we do with E?
Pop up E.
Pop out E? Can you just briefly justify why we should really pop E off the stack?
Because it's the active one. It's the most active vertex right now.
Yeah, I agree. E is now top of the stack, but why should we decide to pop E off without making any further progress from E? Why?
Because it's the ancestor of F.
Not quite. You can see from, okay, I can see you're going on the right direction, but let's now justify it a bit more precisely, okay? So what we have is E here, top of the stack. We can either go this way here or this way. That's the only two outgoing edges, but we have handled them both. Nothing else left. So we should really pop it off, change its color to be black. Right here. And then we're going to remove it, pop it off, and then increment the counter to 10. And then we're going to have A, D, right? E is now the new vertex that has just become black. Okay, that's good. We're getting very close. Let's just make sure yeah, okay, good. Judy, I'll call you the second time. Go ahead. What should we do?
Go from D to F.
Go from, okay, that's good. I agree. So because there are only two outgoing edges there, D to E or D to F, but D to E is already handled. That's good. What kind of edge is that, D to F?
Forward edge.
Forward edge? I agree. That's good. Good, good. Awesome. All right. Okay, so this one here, we don't need to increment the counter. It's not discovery, or it's not popping off. So what we do is we're going to have right here D to F right here, and it's going to be 11. Okay. And D to F turns out to be a forward edge because you can see that D to F is to some descendants. So that'll be forward edge number 2. Okay. So we got forward edge number 2. And we have identified that when t is equal to 10. D to F. Okay, and then let's briefly justify very quickly. Okay, so we'll go from D to F. Okay, so that's F2. So we got DF is actually a forward edge because when you go from D to F, the discovery time for the destination is strictly larger than that, and this is already finished. All right, that's a definition. Good. So we got the discovery of F is strictly larger than the discovery of the source, D. That's why it's a descendants. And also the descendants F is already finished. Okay? Because you can see that it's already black vertex. Okay. And that one there, let me just put a very quick notes over here. So that one there is forward edge. Okay. Anybody who want to be called the second time? Or you want to, oh, actually, that's good. Go ahead.
We pop D now, right?
We pop D away. How come? Briefly justify.
We'll go into E and we go into F.
Yeah, exactly. We only got 2 outgoing edges, right? We have run out of the outgoing. Thank you. Pop it off. Awesome. Okay. Yeah, bear with me. I think we can just finish this example completely. Okay. So we got, actually, we're going to, for the top of the stack is D, right? Handle both outgoing edges already. So pop it off. So going to pop D off right there. And then we're going to increment the counter over here. And then it's going to, so A is the only one. That's great. That's in the stack. So C, B, F, E, and then D. All right. And then let's record the finish time. So for D here, it's going to be 11. And by the way, for E, it should be 10. I forgot to record it, right? Yeah, that's something just from the previous iteration. Okay. Since I've got one last row, who would like to be the last one to let everybody go home? You better be right. Yeah, go ahead. Yeah.
You backtrack on A.
Yeah, I like the term backtrack on A. Briefly justify. Yeah.
All of the outgoing edges have been handled.
Yeah, we got only 2 outgoing edges to B and to D, right? It's done. Good. That's right. Okay, let's finish that. And then I can make some general remark, and then we're done. Okay, so we're going to actually pop off A because all the outgoing edges have been handled. Okay, pop it off. And then we're going to increment the counter over here. So that means A being currently the only gray is going to be also turned black. Okay, so what we do is we're going to say C, B, F, E, D, and also A. And that one there is going to be the change, right? And then, of course, I forgot to turn D when we pop it out. We should really turn it to black. I just forgot, right? And also A here as well. So both of them will change their color. D here, A here. So at this point, you can think about all the vertices have become black. But typically, if you imagine that you're doing your depth first search iteratively, you have a while loop. You would say while the stack is not empty. So as soon as it becomes empty, you can now exit from the loop. Right? So we are done for the current run. Okay. So I think that the second example is a little bit more complicated. You can see more instances for each edge. I think that's very nice. So before we resume on Monday, right? So you will need to make sure you can redo the 2 exercises on the directed graph. I'll give you maybe something even more complicated for assignment. You can practice more, right? So you want to just definitely make sure to look at the back edge, forward edge, and cross edge to see the difference. And also, especially, I think that this way is really nice for you to judge visually. I think that's really the best way to see what's the DFS tree so far. You can see clearly to ancestor, to descendants, or to some non-descendant, non-ancestor. But we're going to focus more on Monday when we come back to see the relationship between the F and D, between different vertices, and also their color. And we're going to see some mathematical property. That's something that can be more algorithmically implemented in Java. All right, that's it. Okay, enjoy reading week. I'll see you back.